I'm going to be presenting some work that I've done in my multi-hatted role. So I'm a professor here at CU in the Department of Atmospheric and Oceanic Sciences. I'm also a fellow in the Renewable and Sustainable Energy Institute, and then I also work at NREL, the National Renewable Energy Laboratory. My group, my research group, the students who I work with and the postdocs with whom I work, we focus on understanding how the atmosphere and wind energy interact. And it seems obvious that when the wind blows a lot, then wind turbines will generate more power. But there are many complications to that that are very interesting if you're into fluid dynamics. And they're also very interesting if you're trying to understand how we can maximize the amount of power that we're generating from the wind, as well as reduce the cost of energy. So I'm going to be discussing several different measurement campaigns that we've been conducting in the last few years. Here in Colorado, we've used data from wind farms in the western United States as well as from the central United States. And then I'll be discussing briefly some of the modeling studies that we've been doing as well. Now, listening to you all, this is kind of nice when you're up in front of the room to actually know a little bit about the people in the room. There's a very broad spectrum of skills and experiences and insights. So it's entirely likely that I'll use some terminology that is not clear to everyone. If that happens, and I will try to explain everything very well, but if that happens, please stop me and ask questions, because I'd rather that we have a discussion and people learn things and you share your ideas with me and I'll share my ideas with you. Okay, is that fair? Okay, very good. Excellent. So, a wake. This is supposed to be a picture of a rock, and we have some water flowing over the rock, and then we have some interesting character in the water on the downwind side of the rock. I don't know how many of you get the chance to go sit and watch water flow in Boulder Creek. None of us probably get to do that enough. But this is the idea of a wake, that flow goes past an obstacle, and then the flow after the obstacle, downstream or downwind of the obstacle, is slower than it was upwind, and it's more turbulent in the wake. Now, the same thing happens when we think about wind energy. So we have atmospheric flow coming into a wind turbine. The flow has some set of characteristics. It may be very turbulent, it may be very laminar or very smooth. But once it goes through those blades and the blades extract a lot of momentum from the atmosphere, the flow in the downwind region is going to be slower and more turbulent than it was upstream. So even during the day, even when we have very strong convective heating that makes the atmosphere bubble up, and we have a lot of strong turbulence, you can quantify how much more turbulent the wake is compared to the upstream flow. So we care about wind turbine wakes because they're beautiful and interesting fluid dynamics, and we can do lots of fun things with observations and with models to simulate them. But we care about them because if you happen to be a turbine located downwind of an upwind turbine, then you're going to be generating less power, and you're going to be experiencing increased turbulent loads in the wake. So if you look at data from large wind farms, it's very common that the turbines in the center of the wind farm break more often, have more issues with loads and that type of stuff than the turbines that are experiencing the uncontaminated flow or the smoother flow on the edges. Does that make sense? So when we think about the flow coming into a wind farm, and now we're looking down on top of an individual turbine in a simulation of atmospheric flow within the wind farm, we have some very complex evolution. So again, I want to emphasize the fact that when we have reduced wind speed and increased turbulence in the wake, that has a very significant impact on the profitability of that wind farm. So understanding wakes is very important for understanding the total amount of power production that you will have eventually, as well as understanding the operations and maintenance costs for operating wind farms. And the characteristics of the wake are something that we want to be able to quantify. We want to quantify what the wind speed reduction is and what the turbulence enhancement is and what the size and the magnitude of the wake actually is. And when we analyze those data carefully, we can see that they depend quite a bit on the background level of turbulence in the flow. So in the picture here, the colors represent the wind speed in this simulation, which is just a slice of the atmosphere at hub height. And so you can see that the free flow atmosphere is pretty fast, 5, 6, 7 meters per second. And then in the wake, we have greatly reduced wind speeds. So we have cooler colors of blue down to 1 to 2 meters per second. Now, something that's kind of interesting here, if you look very, very closely, is that very close to the turbine, within 1 or 2 rotor diameters, sometimes 3 rotor diameters, the wake actually has 2 parts. And so this near wake structure where we have this double lobe in the wake is very interesting, but that often decays and goes away by about 3 rotor diameters downwind. And we can measure this and we can quantify it and we can understand that process. Okay, any questions about this so far? Okay, very good. So we ultimately want to decrease the cost of wind energy and ensure that it is viable and productive, and then eventually get our power grid to a point where wind energy is providing a significant percentage of the electricity that we use in this country. So we think that understanding wakes is very important, because right now, when we try to simulate wakes, either to anticipate how much power will be produced at a wind farm or to think about how to control a wind farm, the wake models that we have a lot of uncertainty in them. And because of that, our wind farm layouts, recognizing that there are lots of other considerations beside wakes, our optimization of wind farm layouts can't really be done if we don't understand wakes very well. And so, this is the mantra of a professor: more data is required. We must go collect more data. So that's what we've been doing so that we can eventually improve these models to optimize wind farm layouts. There have been a lot of very exciting developments in measurement technology in the past 5 years. When I came to CU in 2010, it was very cutting edge to have one LiDAR that looked straight up into the atmosphere with its laser beam and could give you wind profiles. Now, those are very simple instruments. Many groups have them. And we're now using scanning LiDAR, where we have lasers that go back and forth horizontally and can give us very detailed information about the flow. So I'm going to show you some of those observations. And we will, as a field, continue to be innovating on those developments. When we use these scanning remote sensors, we can get very fine and very detailed information about the wake without actually interfering with the wake. If we were to set up meteorological towers, A, that would be very expensive, and B, we would actually be disrupting the flow that we are trying to measure. So using scanning remote sensing techniques is very important for understanding wakes. And now that we have these huge data sets that are emerging from scanning remote sensing devices, we need to develop quantitative and repeatable methods to extract the information we need from these large data sets. So again, we want to ultimately reduce the cost of energy. One of the developments that's kind of out there, maybe 3 to 4 years in the future, is that once we understand wakes, we have the potential to start manipulating them. So we can adjust the pitch of the blades, we can adjust the yaw angle error of the turbine, so that we can perhaps change which turbines in the 2nd and 3rd and 4th and 5th rows experience the wakes and experience those damaging loads. But we can't do that until we have a really good modeling tool that lets us anticipate what wakes will actually do. And then when we're planning wind farms, we would like to have extremely accurate wind resource assessment. There's a lot of uncertainty in that process now. And one of those issues that cause a lot of uncertainty is the issue of wake impacts. And if we can have more resolution or less uncertainty in that respect, then we can probably reduce financing costs. And those of you who work in the industry can probably tell me much more about proper ways to reduce financing costs. And so if you'd like to come talk to me about that afterwards, I'd appreciate that. Or if you have a comment to share now, that would be great as well. So this is the outline of the presentation that I'm giving tonight. I've explained to you now why we focus on wakes in our research group and why so many agencies are trying to fund research on wakes. Next, we'll step through understanding which characteristics of turbine wakes are actually important, and then we'll get to look at some of the fun new observations that we've been collecting, and then we'll look in general at different ways of simulating wakes. So I mentioned before that the near wake has different characteristics than the far wake does. This is one way of looking at that. So we're looking down on top of a turbine. These are the blades of the turbine. And in the near wake region, we have this double lobe structure. These red lines are meant to signify the amplitude of the velocity as it flows through this panel. And so you can see that there's a significant wind speed deficit about halfway down the blade. And this is because that's where the most lift is experienced on the blade. It's not at the tip, it's not close to the nacelle, it's in the middle of the blade. But as background atmospheric processes occur, specifically turbulent mixing, these two minima in the velocity end up merging into one kind of Gaussian-shaped profile in the far wake. So if you're very interested in understanding what happens close to the turbine within 2 to 3 rotor diameters, it's important for you to understand the near wake. But if you're really focused on downstream, downwind turbines, in terms of their power production and in terms of their turbulent loads, the far wake characteristics are probably most important for you. And the other thing that you can notice from this schematic figure is that the wake deficit that we see here in the center of the wake, the difference between the ambient flow and the wind speed at the center of the wake, that deficit starts to decrease and the wind recovers as you move farther downwind. Now, how many of you have looked at observations of wind turbine wakes before? Okay, what is the longest downwind you've ever seen a wake in observations or in simulations?
Kilometers.
Sorry?
Kilometers.
Kilometers. Okay, so that would be, what, 20 rotor diameters? Yeah. So there's a lot of literature that suggests that maybe after 10 rotor diameters, you don't need to worry about turbine wakes anymore. And one of the things that we've been focused on is saying, well, actually, in certain atmospheric circumstances, wakes can persist for kilometers downstream. 20D is not out of the question. And when you have aggregations of wind turbines together, you can see a wind farm wake that extends even further downwind. So I'm foreshadowing here what I'll be talking about at the very end of the talk. So keep looking for that in the future.
I would assume the turbine cell doesn't necessarily correlate directly with the deficit.
That is a very good point. So the comment was that the turbulence enhancement that we see in the wake may not decay at the same rate that the velocity deficit decays. And that's exactly true. The turbulence enhancement tends to break down much faster than the velocity deficit does. So even though you may be able to detect a velocity deficit far downwind, you will probably not be able to detect a turbulence enhancement downwind. But we have detected them at least 6 rotor diameters downwind. So, okay, other questions? Bill?
Can you speak at all to how the weather changes the behavior of the...
Yes, yeah. But maybe I can foreshadow that here now. So we know that the atmosphere has a strong daily cycle, especially here in the United States. In parts of Northern Europe, the diurnal cycle is not as strong, but once we started building large wind farms in the United States and in other areas where there is this strong cycle of solar heating of the ground, introducing convective turbulence during the day, and then that turbulence disappears at night when we have a cold surface and the development of an inversion layer, these strong cycles in background turbulence have a big impact on how rapidly the wake tends to decay. So I'm noting here that turbulent mixing is the process that makes these two minima merge together. Turbulent mixing is the same thing that causes this dip in the wake to eventually erode. Momentum from outside of the wake gets mixed in so the wake can recover. And so if there's a lot of background turbulence helping that mixing along, then this wake will recover faster. So I'm guessing, Bill, that the 20D wake that you have seen was a nighttime stable layer case. And the long ones that we've seen downwind are also from that type of situation as well. And we can replicate that in the modeling world. So here's a simulation where we just are looking at velocity deficits across a wake. So this is a simulation that was done in WRF LES with a generalized actuator disk. Does anyone know what WRF is? Does anyone not know what WRF is? Okay. Okay, good. Wow, this is exciting. So WRF is the Weather Research and Forecasting Model, and this is a numerical weather prediction model that's used all over the world. When you get a forecast from the National Weather Service, WRF is behind it. So we chop up the atmosphere into cells, we solve equations for each cell, and then we get predictions of temperature and pressure, relative humidity. We use parameterizations to represent cloud microphysics and long-wave and short-wave radiation processes. When you're looking at numerical weather prediction, you're typically chopping the world up into 1 kilometer cells or larger. But if you want to represent turbulence more explicitly, so if you care about the three-dimensional nature of turbulence and not just the vertical mixing of turbulence, then you need to use large eddy simulations. And so they're trying to represent the actual eddies in the atmosphere. And so collaborators, Jeff Maroka at Lawrence Livermore, Branko Kosovic at NCAR, myself, and Matt Aitken, who is a graduate student who graduated just this week from me, and he's already moved on to his postdoc at the EPA. We were using this model to look at the nature of wakes in simulation world, where we can control the atmospheric stability to better understand what's happening. So as you've been watching, when we're close to the turbine location, so X here denotes the distance from the turbine, we have a double wake. And then as we retreat further downwind, as noted by X here, then the wind speed deficit, the magnitude of this dip, starts to decrease, simply based on entrainment of other momentum outside of the wake into the wake area. So again, the turbulent mixing is what causes the ambient flow to be entrained into the wake. And although we briefly have a two-lobe structure in this simulation, it's gone by about 2 rotor diameters downwind. Does anyone have any questions about this?
Why is there on the left side of the plot versus the right side of the plot, there's a little, like where it's less disturbed, there's a little bit of a delta?
So there's a little bit of a difference given the rotation of the turbine. And I actually don't remember if we're looking at this as if we were the flow or if we're looking at the turbine from the back. We could probably figure it out just by thinking about where we should have the larger deficit. But it's due to the rotation of the turbine. And not our group, but another group did some studies where they used this type of modeling tool, and they included rotation and then they took rotation out, and it makes a really big difference. So if you're trying to represent the effect of a turbine, you need to include that rotation into your simulations. So we did that.
Does this work LES?
This is WRF LES.
I'll give you the detailed modeling for the wake itself.
So WRF LES, when you download it from NCAR, does not include this generalized actuator disk. That's a development that's not quite ready for prime time right now. So when we've developed it and we've been working with it, we can kind of work around some of the bugs that you have in any code. But before it's released to the public, there's a lot of work that has to be done to make it more general. But the eventual goal...
The part that models the details of the wake, of the individual wake.
The part that models the details of the individual turbine is this generalized actuator disk. And that, again, our goal is to have it eventually released to the public, but it's not there yet.
And what's the theory behind that?
This goes back to the idea of an actuator disk, and you look at the drag on the different elements. So you actually resolve the blades, you resolve the component of the flow that is, you have the tangential and then you have the radial components. You break all of these things down within every individual grid cell. So this simulation used 5-meter resolution. And so we had 3 different components of the drag that the turbine is exerting on the flow at each grid cell. And they all had to work together as one integrated turbine.
Is that drag then a result of the detailed modeling of the flow around the blade?
It is not representing the blades, it's representing the effect of the blades. So we need to know the blade shape, we need to know the chord lengths, or the average chord length within every grid cell. We need to know the thrust coefficient, the power coefficient for the turbine, and all of that, but we're not representing the blade itself exactly. You would need to use an actuator line model to do that, and that does not exist in WRF as far as I know right now. So, does that answer your question? Okay. All right. So what I wanted to emphasize here is that it's very important for us to know the wind speed deficit within the wake. It's also important for us to know the width of the wake and how the wake itself meanders as it moves downstream. So in this schematic, the turbine is located up here. And for this case, probably because of background turbulence, the wake itself does not propagate directly downwind as it did in the idealized examples we looked at before. It's meandering because there are larger scale atmospheric circulations that are advecting it along. So if you imagine a plume from a smokestack, there are a lot of similarities between smoke dispersion and wind turbine wake dispersion. It's not a perfect correlation because the turbine itself has its own rotation and its own turbulence, but there's a lot that we take from the dispersion community, atmospheric dispersion community, to understand wakes. So when we look at data, we want to analyze the wake center line so that we can quantify the meander of the wake, so that we can think about turbines that might be located downwind and whether or not they're going to be in a full wake or if they're going to be in partial wake. And the structural engineers here might get very alarmed thinking about a turbine that is experiencing a partial wake, because the change of wind speed across the rotor disk in that case, when you have a partial wake, is typically exceeding what the turbines are designed for. So you could have 12 meters per second on this side of the rotor disc and 4 meters per second on this side. And the blade is happiest when it's 12 meters per second all the way around, or maybe even higher, 15 meters per second. So wakes are important. I hope that I've emphasized that enough. Okay, so the wake characteristics that we want to know are the velocity deficit, how wide the wake is, how much turbulence we have enhanced within the wake, and exactly where the wake centerline is and how that changes as the wake propagates and evolves as it moves downstream. Okay, so now let's start looking at some of the fun observations. And in putting this talk together, I felt like I was cheating you if I didn't show you this, but I didn't want to have you try to be here for 2 hours, so I had to cut it all down. So let me just say right now that our group and many other groups have been doing some pretty exciting things the last few years in terms of observations of wind turbine wakes. So if this is exciting to you, please write down the references that I'm putting at the bottom of the page, because there are many more details in other papers. So I wanted to mention 3 different experiments to you. Some of you may be familiar with some of them, especially the one that happened here in Colorado at the National Wind Technology Center. This is a collaboration between CU and NOAA and NREL and Lawrence Livermore National Lab, where we used NOAA's super high-powered, one-of-a-kind scanning LiDAR instrument called HRDL, the high-resolution Doppler LiDAR. So it basically takes its laser beam with incredible resolution along the beam, 30-meter resolution along the beam, and typically 6 to 7 kilometers range, although they can get up to 13-kilometer ranges in certain cases. And we used this to both scan horizontally across the turbine and vertically across the turbine to characterize the wake from the Siemens 2.3 megawatt turbine at the NWTC. This experiment happened in the spring of 2011. In fact, it was still going on at the end of April, and we were hoping that the wind would hold on for just a few more days so that we could get more data, although right now I find myself hoping that the wind would just stop and we could get to summer already. Many of the results from the TWIX experiment are in Matt's paper that came out earlier this year. So this is Aitken, myself, Bob Banta at NOAA, Elena Pachugina at NOAA, describing the experiment in detail and then some of the big picture results from that experiment. I'll highlight some of that here. The second experiment that we'll talk about is an experiment that we did not design. A very forward-thinking wind energy company, a developer, had some data that they had collected from a scanning LiDAR that they had put on the nacelle, on the hub of a turbine, looking at the wake downwind. And this is an incredible data resource. They talked with me and they talked with Matt about the measurement techniques that we were using and asked us to analyze their data. So we happily agreed to do that. And this paper just came out last week online discussing what we learned about wakes from the vantage point of the nacelle looking backwards. So some of you may be familiar with putting a LiDAR, a very large laser, forward-looking on a turbine, and people do that in order to anticipate the flow coming into the turbine and adjust the turbine operations to maximize power production and reduce loads. But this is the opposite. We're looking backwards, and this is not a picture from the measurement campaign that we did. This is an offshore nacelle mounting. But due to a non-disclosure agreement, we can't identify the company or the wind farm that we were looking at here. And then finally, I'll talk most of the time today about this experiment called CWEX that we conducted in Iowa last summer at a large wind farm. Some people here got the pleasure of going out to Iowa and lifting heavy instruments in the 100% humidity and 100-degree temperatures. The primary focus there was on what happens with wakes from multiple turbines. So we're going to look at some information about that. We also had more than 1 month of data there. And if you were at the European Wind Energy Association meeting earlier this year, we gave a presentation outlining those results, and the paper should be submitted very soon. So I don't want to leave you with the impression that this is all that's been done in turbine wake measurements. There are a lot of groups looking at turbine wakes at Minnesota. There are 2 really strong groups in Switzerland, and of course several groups in Denmark looking at them as well. So if you want to know more, there's our work, and then there's a lot of other work to explore as well. Okay, so TWIX, this is where we were studying the Siemens 2.3 megawatt turbine at the NWTC. We've wanted to ask a set of questions. How far downwind could we see a wake? How does the wake meander and spread? Does it intersect the ground? And if so, how far downwind does it? That question was motivated by some comments from farmers in agricultural regions where there's a lot of wind energy deployment. And they wanted to know what's going to happen to my crop when all this turbulent air hits the crop. And the answer is nothing, but we needed to measure that and observe that and discuss it. So we'll get to that a little bit later, but that's where that question came from. And then we wanted to do some modeling studies to verify and validate our modeling tools for representing wind turbine wakes. So we deployed NOAA's LiDAR, and we characterized the inflow to and the wake from the turbine. So this is actually an important point, because when you're trying to understand the wake, you have to compare it to something. So you typically have to measure outside of the wake so you can quantify the wind speed deficit. And it's also helpful if you can measure upwind from the turbine as well. And this is, again, another strength of scanning instruments that let you measure the entire volume of a flow rather than just 1 or 2 points as you would with a tower. Okay, this is a picture of NOAA's LiDAR. This is not a picture of the Siemens 2.3 megawatt turbine, but it's a requirement that all pictures from field experiments be as photogenic as possible, so hence the flat irons. All right, so here's the map of the site. Those of you who work here will recognize everything, but this is our turbine of interest. This is one of the Met towers that we ended up using. If you've been out to NREL recently, you've seen that there are 2 new 135 meter Met towers that are beautiful instruments or beautiful platforms for meteorology. Unfortunately, they were not operational at the time of this experiment. So we used the 80 meter tower at the far western end of the site. The LiDAR was located here so that it could scan through a volume that included a profiling LiDAR as well as the turbine. We had a SODAR in that domain as well. And given the nature of the flow at the wind site, this is a representation of the windrows showing you that when we have strong flow or higher velocity winds, so this is 0 to 24 or 0 to 34 meters per second, strong winds at the wind site are almost always from about 292 degrees west-northwest. And so we designed the experiment anticipating flow coming this direction. So that way, Hurdle could scan across this volume, capture the SODAR, capture the LiDAR, capture what was going into the turbine as well as coming out of the turbine. So here's an animation with the same orientation. The LiDAR is up here. This box is the turbine location, and then the cooler colors, the blues and the greens and the purples downwind of the turbine show you the velocities, the line of sight velocities downwind in the wake. And I like this animation because it shows you how much the wake moves back and forth. This whole series takes 10 seconds in your time, but it took about 2 hours to collect. So there's a lot of variability. Those of you who are looking very carefully at the timestamp will notice that this is in UTC time, so this is a little bit before midnight. So we're definitely into the nighttime stable boundary layer. And you would not expect this degree of meander at night. But because the National Wind Technology Center is very turbulent, then we did have quite a bit of meander. So atmospheric scientists have a habit of liking to show colorful pictures and not necessarily giving you all the quantitative information that you need. So one thing that we thought was important to do was to analyze all the types of scans that we collected, both the horizontal scans, so the turbine is located here and it's scanning horizontally, and the vertical scans where it looks at the turbine and profiles straight up and down. So we needed to develop a quantitative approach to extracting these needed weight characteristics from the data. And so that method is outlined here in this paper that just came out earlier this year, where we propose statistical models and statistical tests to verify which of these models fits the data best. And then we can extract the variation of the wind speed as we move downwind and the variation of the wake width and so on. So instead of going into the equations, I thought you might prefer to look at pictures. So the aggregation of our results shows that the results that we collected in Twix, as we look at the velocity deficit as it moves downwind, are within the envelope that's defined by the previous studies that have been done using LiDAR or SODAR or unmanned aerial systems or kites or meteorological towers. But we have a lot of variability, as you can see in this light green envelope. That variability is due to the fact that the NWTC is very turbulent and that we were sampling during the day and at night in a wide variation of wind speed regimes. We only sampled during certain wind direction regimes. And in these two plots here, we try to explain where some of that variability comes from. So when I say region 2 and region 3 of a turbine, does anyone know what I mean? Okay, so just a few people know what I mean. So there's not a chalkboard. There's no chalkboard. It's a classroom. There's no chalkboard. Okay, so power curve. A wind turbine power curve shows you the variation of power production with wind speed. As wind speed increases, the power production also increases until you get to a point where the turbine is generating the maximum amount of power possible. And so that means that even if the wind speed increases, the blades pitch more and more and more so that the power generated is the same, and that reduces loads on the turbines. So region 2 is where the power is increasing as wind speed increases. Region 3 is where the blades pitch to minimize the blade interaction with the flow. And so what we see is that in region 2, where the turbine is extracting as much power, as much momentum as it possibly can from the flow, then we have larger wakes. But in region 3, where the blades are pitching, we generally have weaker wakes on average. But by the time you get to about 5 rotor diameters downwind, you can't really distinguish the difference between the two of them anymore. The background plays the trump card in that circumstance.
But is it true that in region 3, the power extraction is generally higher than region 2?
So no, actually, if you look at the power coefficient is at a maximum right before you get to region 3. So the blades, instead of being flush against the flow, are pitched so that they're not extracting as much power. So the magnitude of the wake deficit will decrease as wind speed increases after you're past that transition from region 2 to region 3. And someone from GE, not someone who was here, but someone from GE a couple weeks ago told me that they don't actually talk about region 2 and region 3, but region 2.5, because funny things start to happen at the shoulder. So this is, in an atmospheric science publication. So for the engineers who might be irked at this terminology, I think that's probably sufficient. But the atmospheric scientists like to get excited about atmospheric stability. So again, nighttime is stable. There's not much background turbulence. Daytime is unstable. There's a lot of convection. And what's interesting is that we expected to see a very large difference between nighttime stable and daytime unstable conditions. And we did not see that at the NWTC. And we think that the reason for that is that there's a lot of complex landforms just upwind of the NWTC. So even though we have a stable situation, the site itself is extremely turbulent. So what may be considered stable from a temperature profile perspective, it may not actually be stable from a background turbulence perspective at this site.
And Julie, you were primarily focused on northwest wind cases too?
Yes.
So that would also lead to that mixing?
Yeah, because 5 kilometers upwind from the turbine is El Dorado Canyon, and then just before that is the peak of the Rockies. So yeah, there's a little bit of complex flow in the environment. Yeah. Was there another question over here? Okay. So let's shift gears from Colorado and go to someplace a little bit simpler. This is Iowa, which does not have the terrain features that we love so much in Colorado, but it does have a lot of wind energy. Iowa is getting, I think, 26% of their electricity from wind now because they have such a tremendous resource and a large number of very large wind farms. So we collaborated with a group from Iowa State and the wind farm owner-operator to design a series of campaigns in this wind farm in central Iowa. CUX-13 is only the latest in a series of experiments that started in 2010. You can get more information about the other studies in Dan Rayevsky's outline in the Bulletin of the American Meteorological Society. And then Mike Rhodes, who got his master's degree working here with us at CU, has some LiDAR measurements that he presents here in boundary layer meteorology as well. So we were trying to quantify how atmospheric stability in a region where we have very strong diurnal changes in stability will affect wind turbine wakes. We were also interested in looking at other more kind of weather weenie phenomena like the nocturnal low-level jet, which is this really exciting acceleration of the flow about 100 meters above the surface that happens almost every night in the summer in the Midwest. And then we wanted to look at the turbine power production data to tie the atmospheric response, or to tie the atmospheric input to the turbine response. And then of course there's always modeling studies that we need to do to generalize our observations. So here is a schematic of the region of the wind farm where we were focused in this particular summer. The dots represent turbines, and those of you who have done wind farm layouts might have some thoughts as to why this turbine is not in line with all the others, perhaps due to a house nearby. Same thing down here. And the landowner participation in the wind farm probably led to this kind of patchwork as opposed to the nice regular grid that we would expect to see. But this is a great location for atmospheric studies because in the summertime, the flow is almost always from the south. It's very predictable, so we can design our instrument layout appropriately. So here is a measurement of the winds at 200 meters over the time that we took our measurements in 2013. So again, the colors, as you would expect with the windrows, represent the wind speeds, 0 meters per second up to 18 meters per second. And you can see that most of the mass in this windrows is southerly, southwesterly flow. Now, if I showed you the windrows for 40 meters above the surface, it would be a little bit different. Most of the mass would be down here. And so remember the fact that the wind direction might change with height, because that has some interesting implications. So we designed our experiment to put all of these other surface flux stations where we're measuring the exchange between the surface and the atmosphere at these green spots. We used my groups and Bill and Sue's groups profiling LIDARs to measure the wind profiles, upwind of the first row of turbines, between 2 rows, and then after a second row of turbines. And then for part of the summer, we had this red instrument, which is called a 200S, WindCube 200S scanning LiDAR. So this is similar to the NOAA high-resolution Doppler LiDAR that I showed you before, but it's a commercial product that Leosphere provided to us. We were also able to have temperature and moisture profiles from a radiometer. Radiometrics is a company here in Boulder, and we were grateful to use their instrumentation as well. And then Iowa State measured surface fluxes. So we have a lot of information about what's happening in this wind farm so that we can measure the wakes and quantify them. When you're measuring hopefully similar things with the same instruments, it's important to verify that they are all measuring the same thing. So we had a short intercomparison campaign where you can see the very photogenic turbines in the background and our even more beautiful instruments in the foreground. They all agree very well. And then we moved them to their separate locations after we verified that everything was working appropriately with them. So I alluded before to the fact that when we look at our measurements at 200 meters, we see something different than what we see at 40 meters. And so let's look very carefully at the primary wind direction at 200 meters. So it's more southwesterly, south-southwesterly, whereas at 40 meters, it's really a southerly flow case. So I've talked a little bit about stability and I've talked about background turbulence, but I may not have reminded you of the fact that at night when we have stable conditions, there's very little communication between the surface and upper levels. And so it often happens that there's a change of wind direction with height. And that has very interesting implications for what could happen to a wake if it's in a flow that's changing direction with height. So think about that. I just wanted to verify for you that we have a strong diurnal cycle in temperature, and that gives us a strong cycle in atmospheric stability. So these data, because the Obuchov length is greater than 0, we would say that this is a stable situation. Because it's less than 0, we would say that it's an unstable situation. And because of those variations in stability, we have a response in the winds. So this is just one example of one night. So we're looking from 0 UTC to 24 UTC, which is really 6 p.m. local time to 6 p.m. local time the next day. And on the top, we have color contours of wind speed. And on the bottom, we're looking at wind direction, which is not really projecting all that well. But let's look at wind speed. You can see that at any given point during the night, if you move up, then you're going from relatively low wind speeds, 4 to 6 meters per second, to around 12 meters per second at hub height, which is noted by the solid line. And then by the top of the rotor disk, you're getting up to 14 meters per second. And if you were able to go even higher, you'd be encountering wind speeds on the order of 20 meters per second. This phenomenon, the nocturnal low-level jet, happens almost every night in the Midwest in the summer. It happens very often in other seasons as well. The magnitude of this acceleration and the height of the acceleration changes from night to night. It has a lot to do with different air masses moving through, the effect of the sloping Great Plains, changes in baroclinicity and the thermal wind and that type of stuff. But the low-level jet is very important for wind energy because it provides a lot of the wind resources. And when it penetrates lower into the rotor disk region, then it can have some pretty serious consequences. Because along with this strong acceleration in winds, there's also a change of wind direction with height that's not clearly noted here since you can't see the color differentiation, but we'll see again on a subsequent plot that there can be changes on the order of 20 degrees across the rotor disk. Now, does anyone know what the International Turbine Design Standard is for changes of wind direction across the rotor disk? What are turbines supposed to be designed for? It's not 20 degrees, it's like 4 degrees. So this probably explains quite a few of the problems that they have in wind farms in the Midwest in terms of blades breaking ahead of time or ahead of schedule and other issues with loads and that kind of stuff. It's a meteorology problem that needs to be accounted for in the design. So here's one of the nights that I really enjoy looking at. Again, we have wind speed on the top, we have wind direction on the bottom, and here we have a time series for the first 16 hours of the night for the wind direction at 40 meters above the surface, so the bottom of the rotor disk, for 120 meters in blue, that's the top of the rotor disk, and then 200 meters above that, just because we had the data and wanted to see it. And so again, you can see that we have 30 degrees in this particular case when we're at wind speeds between 6 and 10 meters per second, which is in the steep part of the power curve where the turbine should be generating a lot of power. Not maximum, but it's on the increase. And this is 30 degrees across the rotor disk. So this is well outside of the bounds of what the turbines are designed for. So I'm hoping that I'm convincing you that meteorology is really important and that it's important to take measurements not just up to 40 meters or 60 meters. 60-meter Met towers are easy to put up. You don't need to have lighting on them. They're relatively inexpensive, but crazy things can happen above there. So it's really important to measure that so that you know what your wind farm is getting into in a certain location. Yes?
In that case, was there any inversion or decoupling in this case? Or was it just varying with?
This was just varying due to the low-level jet. So the inversion was above 200 meters by, I think it was by 4 UTC. So all this is happening underneath the inversion. And we estimated the inversion height looking at the microwave radiometer data. So we just had temperature profiles every 50 meters. So it's a coarse estimate, but even this coarse estimate suggested that all of this was happening below the inversion. That's a good question. Okay, so when you're using a scanning LiDAR, especially commercial product, it's good to check to see how far you can see. And we were able to see typically on the order of 3 kilometers to sometimes 5 kilometers downwind from our scanning turbine. So we could certainly see what was happening at the closest row of turbines and the second row of turbines. So we have a good picture of what's happening in this wind farm. And when we compare this instrument to another instrument, a similar, slightly different instrument co-located with it, even though they're using different measurement techniques, the simple LiDAR took a measurement of the wind profile every 4 seconds, whereas the more sophisticated instrument actually took 3 minutes to make a measurement. The agreement is better than we would have expected for that difference. So we developed confidence in this instrument that I'm about to show you the results from. The differences are mostly during the day when we have a lot of convection and a lot of turbulence, where the time scale difference between 4 seconds and 3 minutes would be very important. So I'm going to show you 2 sets of scans from the scanning LiDAR. So we're looking at turbines downwind. The wind is blowing at us from the LiDAR. And that's due to a lot of the things that you need to put up with when you're designing a field campaign. You never get instruments exactly where you want them. But we ended up being pretty happy with this setup, because if we used a low elevation scan, we could measure our turbines right at the bottom of the rotor disk, at 50 meters actually. And then if we used a higher elevation scan, we could see what was happening close to the top of the rotor disk. And we were interested in seeing what would happen to the wakes due to this change of wind direction that we had anticipated seeing. So these are going to be animations, but I want to orient you to them because they're a little bit different from the ones we looked at before. So first, so the LiDAR is located up here at the top of the pie piece. And we're looking at this row of 4 turbines, and we're scanning on the left at the bottom of the rotor disk. A few minutes later, we were scanning near the top of the rotor disk. Those of you with sharp eyes will notice that, hey, look, there's 2 more turbines here, but they're not really over there. And that's because these turbines are further away, and so therefore we were intersecting these close to the top half of the rotor disc, and we're scanning above those turbines for the most part with a higher elevation scan. So there's those turbines. We see the 4 turbines in the same region again over here. And if you look carefully down here, you can get the time stamp, which is in UTC, which is 6 hours ahead of local time. So
Which direction is the wind?
the wind is blowing from the south-southeast initially. So in this still image, you can see the wakes propagating to the north. So before we were looking at just one of these wakes from the hurdle, and now we see 4 of them together. And we were actually sampling them at slightly different altitudes. So here we're at the bottom of the rotor disc. By this, I think it's by 1,000 meters, we're actually below the bottom of the rotor disc, but there's still some evidence of the wake, which is kind of interesting. Okay, any other questions before I start?
Is this data from hurdle or from the?
This is from the 200S, yeah. And this is the same 200S that Bill Brown was using later in METCRACS.
It would appear that on the left, all the 4 have really merged. You see merging of 2 by 2, and then perhaps all 4 of them.
Yeah, so that's a little bit tricky to interpret. So I can see why you would think that they're merging at that point, but remember that we're scanning at an angle. And so the data that are very close to the LiDAR are taken very close to the ground. So the wind speeds are lower in general. So it's a little bit difficult to say that this kind of light blue is representative of the wakes merging together. That's probably just that the overall wind speed is so low that the whole region looks like that. If you look further above at the higher angle, you can't really see the turbine wakes merging either at that point. So this wind farm was actually very well designed, in my opinion, after looking at these data, because the wakes never end up merging, no matter what altitude you look at. Okay, so enough talk. Let's see the movie. Okay, so you can see that, and I'll show this again a couple times. So you can see that the winds increase over the course of the night, and you can also see that they change direction over the course of the night. And by the end of the night, and it actually starts around 10 UTC, at the top level, the winds are almost westerly, whereas at the bottom, the winds are still southwesterly. So we actually have a wake that's being stretched because of the change of wind direction with height. So imagine if you were a downwind turbine, you're kind of worried about being in a partial wake, but the wake is actually being stretched out. So that's going to exacerbate the problem of predicting where the wakes actually are. So around 6 UTC, we start to see this change of wind direction, and at 10 UTC, it's very dramatic, where we have that 30-degree shift between the winds at the bottom of the rotor disc and the winds at the top of the rotor disc.
So when you say that, you're saying that when we look at the left picture and the right picture, that the wakes are in 2 different directions in the 2.
Yes.
The left and the right.
Yeah.
You see them curve in the right also.
Yeah, and one of the reasons that they curve off is because the data that's collected at about 1,000 meters from the LiDAR is actually lower. So the curving is a representation of the fact that the wind is a different direction at lower altitudes. So we're now actively working on, I should point out something else. You'll notice that there are kind of stripes of colors over here. That's because the LiDAR is no longer perfectly aligned with the flow. So it's only sampling a component of the flow, which is a little bit tricky, but we can still extract useful wake characteristics. So we're using the method that we developed with Matt Aitken to analyze the characteristics of these wakes and then compare that back to atmospheric stability, wind speed, background turbulence, and that type of stuff.
I didn't quite understand your response to the comment about curvature.
Okay, so the LiDAR is looking at an angle. The LiDAR is located on the ground. And even, so you're looking over here at a low elevation scan and over here at a high elevation scan. But the closer you are to the LiDAR in either scan, the closer you are to the ground. And the wind has different directions up here than it does down here. So the curvature, your mind wants to think of it as being at one altitude, but what you're really sampling is on an arc.
So you're saying you scan to the scan at a given distance from the LiDAR, it's a different elevation?
Yes, yes, exactly. And I think, let's see. So that's kind of what this cartoon is supposed to point out, that when you're close to the LiDAR, even the high elevation scan is relatively close to the ground. At the turbine, it's much higher. Okay. So to summarize the results from the CU-X campaign, there are significant impacts from wake flow on power production, loads, O&M costs, that type of stuff. Even in flat terrain, we see interesting phenomena, primarily driven by the daily cycle of atmospheric stability. So we often have very complex profiles where we have wind speed shear changes of 6 meters per second across the rotor disk, and the wind direction changes approximately 30 degrees. So if you're using a power law to extrapolate a 10 meter or a 40 or a 60 meter measurement on up, don't do that if you're trying to do that in Iowa, because it won't work. For the next steps, we are now actively working on quantifying the wake characteristics and how they vary with inflow conditions. And then, of course, we're starting to simulate these wakes so that we can improve the models. We strongly recommend using scanning LiDAR measurements for field campaigns at other sites to understand wakes. Okay, so I did promise that I would show you a few results of simulations. Simulations of individual turbines I kind of already snuck in when we were talking about background of wake context, or the background context of wakes. So I'm going to focus mostly on the impacts of large wind farms on local environments, as we can see through mesoscale modeling tools. So the idea is that the wakes from individual turbines will end up merging together at some point, perhaps depending on your resolution, into a large wind farm wake. And these are large eddy simulations using a different code. This is Matt Churchfield at NREL using OpenFoam, which is another open source community model. And NREL has actually made OpenFoam, their modifications to OpenFoam, publicly available, so anyone can use that. It's a great tool, and it's already out there available for use. So the question is, we have a wind farm and we have a wake extending off, in this case, extending off to the west from the Horns Reef wind farm. And we can see this wind farm wake from satellite observations of the surface wind speed. So if that's happening at the surface, you can imagine what might be happening aloft at the actual turbine rotor level. The very early work done at Risu DTU in Denmark showed that atmospheric stability did have an impact on the wind farm wake. So in unstable conditions, again, we have a shorter wake. They only had measurements at near neutral conditions, but they saw wind farm wakes on the order of 20 kilometers in those near neutral conditions. And they did not have any data to discuss strongly stable conditions because of their location. So the idea is, if this is happening, then we need to be able to represent this in numerical weather prediction models so that we can understand the impacts of wind farms on downwind environments, on agriculture, on other wind farms. And that gets into some interesting legal and economic issues. So for example, this is a map of wind farm development in Iowa. And you can see that there are very large wind farms being built approximately 20 kilometers away from each other. I think that they would like to know if they're going to be experiencing impacts from their upwind neighbors. Similar things are happening in Oklahoma. The spatial scale is a little bit different here. These two large wind farms are within 50 kilometers of each other. And these data are a year and a half old now, so I can assure you that there's been more development since then. And maybe some of you guys could tell me about the developments that have happened in Oklahoma since then. So the idea of wind farms interacting is a real issue, and there are economic and legal consequences to that. And we'd like to be able to understand that from a physical perspective. Dan Caffeine, who's a professor here in economics, and one of his students, Chris Worley, investigated some of the legal and economic issues on wind farm interactions a few years ago. And we've proposed a project where we will follow up on that with a more refined modeling tool, specifically the one that I'll talk about with you now here. But before we talk about our modeling tool, I want to talk about other observations, specifically satellite observations of surface temperature increases near large wind farms. So a group based at SUNY Albany looked at satellite obs of surface temperatures in West Texas, and they were able to observe that during summer nights, and these were only nights without clouds, so they were not able to look at every night because of the nature of the data that they were using, there was a distinct surface warming on the order of 0.2 degrees Kelvin during these summer nights. Other people have seen similar results in complex terrain, and the work that we've done in the Iowa wind farms also agree with the idea of a slight nighttime warming, as well as enhanced carbon dioxide exchange during the day, but not at night. And if you're really interested in the details of how vegetation communicates with the atmosphere, I would love to talk to you about that later. But this is the current state of the knowledge about these types of interactions. So if we want to study individual wakes, we need to use computational fluid dynamics models or large eddy simulations. If we want to look at global climate change, we need to look at global scale models. And so we're suggesting that it would be very useful to look at wind farm impacts using a tool that's kind of in the middle of the road, using a mesoscale numerical weather prediction model, where we have relatively fine resolution and we can represent more physics than we can using a global model. So we have implemented in WRF, the Weather Research and Forecasting Model, a wind farm parameterization. And we call this the Fitch et al. Parameterization because Anna Fitch did a lot of the work on this as part of her PhD work. She's now a postdoc at NCAR. And I'm going to be specifically talking about the results of one of our studies using that mesoscale wind farm parameterization to look at the wake from an idealized wind farm of 100 turbines with a spatial coverage of 10 by 10 kilometers in central Kansas. We used kind of a classic atmospheric science case study to do this, but we did make sure that we had a very strong diurnal cycle. So what we're looking at here is the results of simulations without the wind farm present. So here we have, I believe it's almost 48 hours of data as a function of time and as a function of height. The wind turbine layer is denoted here with these dashed lines, and the colors tell you what the horizontal wind speed is in this regime. So this is just to develop confidence that the model is getting daytime slowdown as the winds are very well mixed, nighttime accelerations in wind speed, stronger wind speeds are yellow, and the dotted lines tell you about the temperature profile of the atmosphere. When we add a wind farm to the simulation, we get some changes, and those changes are a little bit difficult to see when you're just comparing left to right. So we calculate, I guess it's on the next slide, we calculate difference plots. But what I will emphasize here is that in the model world, when we have a wind farm present, we see a slight wind speed reduction, and that mostly occurs at night. And then the nighttime inversion, the dotted lines that you can see here, is pushed up because of the presence of the wind turbines. So now we can start to look at different plots as we look down, as if we were looking on a map at the wind farm. So this little square denotes the location of the wind farm, and we've subtracted the case with the wind farm and the case without the wind farm, so that this wind speed difference here, that's the wind farm wake that we're trying to understand. And you can see that during the day, our horizontal wind speeds are pretty low, and the wind farm wake is pretty small. It's on the order of ½ meter per second as you get to about 30 or 40 kilometers downwind. This would probably not be noticeable in the background context of an atmosphere doing what it does during the course of the day. So if we want to quantify that with an e-folding distance, we would say that it had a 15-kilometer e-folding distance. Night is a different story. So remember, the winds are stronger at night. Remember, there's less background turbulence at night. So there are fewer processes available to mix out the wind farm wake. And you can see that the magnitude of the wind speed difference is much higher. We have a 30% wind speed reduction. And then if we want to quantify this with an e-folding distance, it's greater than 50 kilometers downwind. This is not a real case. These are not real observations, but they're based on the real atmosphere. So we're trying to figure out how to collect the data that we would need to verify and validate this model. There are two approaches that we're taking. One of them is taking actual observations, which is a little bit tricky because terrain likes to modify these types of impacts. We're also using very refined models, the large eddy simulation model that I mentioned before, and we're doing refined simulations to compare to these coarser scale simulations to verify if this is the type of impact that's actually seen. A colleague of ours, Pedro Jimenez at NCAR, has also taken data from a large wind farm off the coast of Denmark and compared these simulation results to the observations of power production there and found reasonable agreement. So if you want to understand wind farm impacts, modeling tools are one way that you can do this. People are often very excited about temperature changes, especially people who work in agriculture. So I wanted to show the difference in the temperature profile between the wind farm case and the no wind farm case. And you can see that at night we have a slight, during the day there's nothing really going on. The boundary layer is well mixed, so even if the turbines make a change, that's diluted over the 1,500 meter depth of the boundary layer, or I guess in this case 1,000 meter depth of the boundary layer. But at night, we do have a warming of about 0.5 degree Kelvin at the surface. The warming is actually stronger at the bottom of the rotor disk region, and that makes sense because that's where the momentum and the warmer air from aloft is being brought down. And then we have cooling in the upper half of the rotor disk because cooler air close to the surface is being brought back up again. So these results are consistent with what we would have expected within the wind farm. We can also look at downwind, and downwind the temperature changes are extremely small. And I think, this is 10 to 20 kilometers downstream. So it's a very small impact on temperature once you're out of the wind farm itself. So I'm not an agricultural meteorologist. I cannot comment on whether or not this 0.5 degree warming is significant or not, but I know that some of my collaborators at Iowa State are excited about this because they think that it would help with certain fungal issues that crops have in the early parts of their growth cycle. And they're also concerned about any slight warming at later points in the crop cycle. So the answer is it depends as to whether or not this is a big deal or not. So there are a lot of questions regarding wind farm impacts, and those questions are only going to grow. We can use mesoscale modeling tools to assess these impacts. If we're looking for wind speed deficits, whether we're looking at an individual turbine or whether we're looking at a large wind farm, those deficits are largest at night. And the surface temperature impacts are on the order small, less than about 0.5 degree Kelvin within the wind farm, as we looked at here. And there's another study that Anna led that's been published in the Journal of Climate, where people who attempt to explore the impact of wind farms on global climate with a simpler representation of wind farms often end up exaggerating and reversing the signs of the impact. So one of our studies, or one of our conclusions from the Journal of Climate study, is that it's very important to put the turbine response at the right level in the atmosphere and not just in the lowest level, which is what you have to do for a global climate model. And then as an observationalist who's become a modeler, I think it's really important that we have validation using real observations of our modeling tools before we start making policy decisions. So we like to go out in the field and make measurements and wear goofy hats and t-shirts while we do it. So I think I will stop here, and you guys have been very animated and paying attention, and I really appreciate that. And I'd be happy to answer any other questions that you have before we go home for the evening. So thank you. Any questions? Bill?
I remember giving a talk once in front of folks who were in the agricultural area, and they were worried about the mixing, or what the mixing would do. But a lot of them thought that if they actually had a slightly longer growing season, that may affect the seeds that they plant or the crops that they put under the wind farms, because they actually have maybe more pollination happening, and maybe another week or two on either side of the growing season, depending on how close to freezing the temperature might get in spring and fall. So they started thinking it's all negative. And then with some of these results, I think they may be thinking that maybe this is something they could take advantage of.
Yeah, perhaps. People in California and Florida have been using big fans in orchards for many, many years. I think maybe even over 100 years, because it was recognized that if it's cold at night, you can bring warm air down from aloft with a large circulating set of blades. So it's reasonable that wind turbines would have that type of impact as well.
The only other comment I was going to make is when you think about a lot of wind farms going up in the Midwest and the friction it causes and slows down the wind near the surface, you have to only go back a couple hundred years before people went out there and started cutting all the trees down the farm. And so, North America had a lot more trees further west than it does now. So in some case, we might be actually reverting back to a time when we had more friction near the surface, although just a little more clustered. Yeah,
and these are trees with rotating branches, so yeah. Yeah, I was thinking about buffalo grazing in large wind farms, like in North Dakota and South Dakota have a tremendous wind resource. And there are a lot of people shifting from farming wheat to farming bison because they can make much more money that way. But that also means that you need more fencing around the wind turbines if you're going to have 2,000-pound buffalo running around. But yeah, we affect the atmosphere in many, many ways. Sometimes we don't realize it. Okay, any other questions?
I'd like to raise a totally out of scope question.
Totally out of scope. Those are always fun.
First, to compliment you on an excellent presentation. Is anyone at CU concerned with environmental impacts of wind, counting of birds, bats,
Yes.
both within the turbines and infrastructure all around them?
So the bat and bird issues, I am not aware of anyone at CU working on that. I know that at Cornell, let's see, Chris, I can't remember his last name right now, but I know that at Cornell there's an ornithology lab. And they, very famous ornithology lab, and they do a lot of work looking at bird impacts. I don't know which, maybe, Catherine, maybe you know, which universities are specializing in bats right now, because the question of the pressure changes induced by the blades and which species of bats that can be an issue for. I don't actually know who the right people to talk to are about that.
Perhaps we take that into
Okay, yeah, perhaps.
It's not just birds and bats, it's all small mammals with large impacts of infrastructure, traffic, like in Texas, for example. There are a lot of desert species.
Yeah, I think it's important to recognize that whatever energy choice we make is going to have impacts. So if you put concentrated solar in a desert environment, that is in some cases good and in some cases bad. If you're relying on coal for power, there's a lot of mercury emissions from those power plants that can have broadband impacts on many, many species. So I've not seen anyone who's done a really good valuation of all the impacts from conventional production as well as renewable energy production, but that's definitely work that should be done.
Part of the reason that I ask is because the funding for all of that really comes from private nonprofits that I personally support. And
Okay.
having more government, university grants focus would be really helpful.
Yeah, there's, I certainly wish that I could dictate the government research agenda. That would make my life a lot easier in many ways. But I know that the American Wind Wildlife Institute does a lot of really good work, and they try to be kind of a connection between industry and academia in terms of suggesting research paths. And they're very focused on understanding wind impacts on avian species and probably other species as well. So, yeah.
I just have a comment. We started forecasting for some of the productions in China, and there's places in China where there are a lot of wind turbines really close together. I wonder whether it's enough high or how the issues.
Okay, so I don't know if everyone could hear Kristen or not, but she said that her company recently started forecasting for China, and many of their turbines are located very close together. And she's not sure if there are low-level jets there or not, but I would say, if the turbines are within 3 to 5D, there are going to be impacts. And one of our colleagues who was at NCARN is now at DNV-GL, or whatever the DNV-Garrett-Hassan-GL merger is. I'm really sorry, I wish this wasn't being recorded because I should have remembered the name exactly. Anyway, Darren Reif did a great global climatology of the low-level jet. And I do think that there were low-level jets, at least in northeastern China. But we can go back and, do you remember? Okay.
I believe there are.
Yeah. Yeah.
And I can get you a map of that.
Okay. Yes.
I have a question regarding the double lobe nature of the near wake. From your models and your tools, I guess, are you able to determine what is actually from blockage and extraction and what is from actual reverse wind flow, like vector addition?
Okay, that's a really interesting question. And with our observational tools right now, we can't diagnose where we can't diagnose which influence causes what with the double lobed nature of the near turbine wake, but we can do that in modeling world. And that was the last part of Matt's PhD thesis, because the generalized actuator disk was really rotating blades without a nacelle and without a tower. And he was able to put in the nacelle and the tower, quantify that impact, which was essentially very small, and so that did nothing at all to the double lobe nature of the wake. But he also put in rotor tilt, So the rotor is not parallel to the ground. It's tilted backwards a little bit to prevent blade strikes. And that makes a really big difference in where the wake propagates as it moves downwind, at least 5 to 10 meters, if you put in an accurate rotor tilt. So I don't know how to answer your question now, but I know that we could try different things in modeling world to see what was able to replicate the results that we need. So that's definitely something that we could talk about later. So thank you. I didn't realize how dark it was back here. Yeah.
What happens when turbulent wind enters a wind turbine? For instance, fluid dynamics would dictate that the larger the object, the larger the wake. So if you had like a mountain range and your turbine's on the other side of that range and the winds come down, and let's say they're already turbulent.
Yeah.
When they enter that wind turbine, is it going to become more turbulent or less? Does that have any effect?
So whatever the wind is coming into the turbine, it's going to be more turbulent downwind. And the degree of turbulence enhancement will probably asymptote at some level, but I have not yet seen a case, even here at the wind site, where the wind was not enhanced in terms of its turbulence downwind of the wake. So it will always be more turbulent. What was the first part of your question?
Yeah, because we have a lot of wind parks, a large percentage of our turbines are on or around mountains. And I was wondering if there was ever an instance where the turbines on the outside of the group would actually take a heavier load than turbines behind. But according to your answer, no.
So one thing that I've seen in looking at data from wind farms is that the turbines on the edge typically tend to produce more power because there's often a little bit of a speed up as you go around. It's not really a bluff body, the wind farm, but there is some acceleration around the outside of the flows. And actually we see that in Anna's simulations as well. If we look at the power production of the turbines, the ones on the edge tend to benefit from that acceleration. So the flow may or may not be much less turbulent on the edges, but they do get that acceleration and that's helpful. And in other studies, we've looked at power production from individual turbines that are at the front edge of a wind farm. And typically, the more turbulent the flow is, the less optimal the power production is, unless there's something else going on. So there have been cases where something else is a strong change of wind direction with height in stable cases. And so then the hit that you get off of the turbulence is not as bad of a negative hit as you get with the wind shear at night. So in general, turbulence is not ideal. It's not what they're designed for. So good question. Jake?
So when you are doing campaigns and you're measuring the wakes out from wind plants that are owned by external entities,
Yeah.
Are you allowed to get the information as far as what the power production is of each of the turbines? Because I do know that it's at least a thought, and I'm not sure how common this is in practice, of derating the front turbines a little bit so that way you actually have better production of the wind plant as a whole.
Yeah. So I have many different arrangements with different companies, and each one is completely different in terms of what type of data they'll be able to give us. But with some wind farms, we do get all the power production data. And one of the reasons we want to get our wake models correct is so that we can give people advice on derating the front row or changing the yaw angle error so that you can actually send wakes in different directions. You can't control the wind direction, but you can control the initial bit of momentum that the wake has, and that might be enough to protect downwind turbines so that you can send the wake in between them, perhaps. That will work pretty easily in cases where you have channeled flow, where you can anticipate the direction. In the Midwest, where the wind direction sloshes around quite a bit, I'm not as optimistic about that. But particularly for offshore wind farms, where you have a very predictable wind direction, when you don't have significant weather coming through. I think that type of optimization and adaptive control, derating or changing the yaw angle, that has a lot of potential for great use. That's a good point.
One other question. Oh, so back to
Yeah, let me just get her real quick.
How long does it usually take, or by what means do you get this information to the IEC?
Oh, that's okay. So the IEC is the International Electrotechnical Commission, and they define the standards for turbine design and for what types of measurements are supposed to be made when you're doing power production estimates and things like that. So Our approach has been to participate in the IEC meetings and make gentle suggestions about what we have learned. We try to be very visible, give talks at lots of conferences so that people who are like leading the standard revision committees so that they know about what we're doing. I'm not interested in doing our research and writing papers that me and 6 other people will be reading. I want people to use this information, and so that's why we spend a lot of effort to go to industry conferences and things like that. So we can't like march into the IEC and say, hey, guess what? We figured out something and you need to respond right away. And that wouldn't be my approach anyway. We just want to put our information out there so that the people who are decision makers and policy makers can use it. And I'm very happy to spend a lot of time talking with people to get that information through.
It just seems like it lags behind sometimes so much that it's hard to account for the advances in technology.
That can be depressing, but I will say that in 2010, I was at an OEA meeting and people were still talking about whether or not remote sensing instruments could be trusted. And now we're doing crazy stuff, measuring turbine wakes, and people are believing it. And I mean, I showed you all of those one-to-one plots for the instruments just to verify that, yes, these instruments are working and that we can trust them. But things have changed a lot in just 4 years. And it reminds me when I was a graduate student, I took, in atmospheric sciences, I took an air pollution law class. And at one point I realized that the law was based on what we knew 25 years ago. And I was like, this is wrong, we can't be doing that. And the professor was like, yes, yes, yes. It takes a while for changes to work through. And I was outraged and I was like, well, we have to do this, we have to do that. But yeah, we should be pushing things forward. But the best we can do is put our insights out there and try to hope that they'll be picked up. So don't be disheartened.
If the deleterious effect of wind shear, wind speed with height, and the variation of direction is sufficiently high, one might think of studies, at least modeling of smaller diameter, like stacking 2 smaller diameter turbines rather than one huge.
So there have been groups that have used modeling studies and wind tunnel studies to think about staggering the heights. So that the first row would have, say, 80-meter hub heights. The second row would have 60. The third row would have 100, and so on. I don't know, and maybe you guys in industry know. I don't know of any wind farm that's actually been built like that. But people are thinking about those possibilities.
With smaller turbine diameters, it would reduce this variation of wind.
Okay. So the recommendation of the smaller turbine diameter that would reduce the shear. But it would also reduce the amount of power that you can eventually collect. Because in the last 2 years, the average capacity factor for wind farms has gone up quite a bit. So now it's, I think, in the high 30%. And part of that is due to the fact that we have larger rotor discs that can still operate even at low efficiency. They're still operating more often. So
do your measurements give an indication of what the efficiency is, the reduction of power due to the wind shear over the large rotor diameter?
We could do that, but we have not done that. It would require data from many different wind farms with many different rotor diameters. But we could do it.
That would be the kind of data when you think we'll go into some trade studies of size of rotor disc or so forth.
Yeah. There's a lot that the wind resource assessment people do in terms of optimizing layouts and turbine choices and things like that.
Let's thank Julie one more time.